SwayamPrabha. Digital India. Educated India.
Welcome to the class of Intelligent Product Design. We have broadly covered all the important elements that you will need in terms of developing an intelligent product. Now is the time for us to first of all take some fresh inspirations from nature, which in this talk I will be explaining to you, and then we will submerge ourselves to some of the case studies. So, in this final goal of our learning exercise, I will talk about first about the intelligent system design. Product is a very specific theme of it, but overall any intelligent system can be based on inspiration from nature. So, I will talk about intelligent system design and how we can take the inspirations from nature. I want to begin my talk from a quote of Leonardo da Vinci, which you all know as a great scientist, engineer, architect and artist as well. Now, Leonardo's one quote is related to design, and that says, human ingenuity may make various inventions, but it will never devise any inventions more beautiful, nor more simple, nor more to the purpose than nature does, because in her inventions nothing is wanting and nothing is superfluous. So, that gives us the inspiration that if we want to design something, a product which is beautiful as well as simple as well as functional, then we must learn from nature. More contemporary, I will quote from Victor Papnek, who talked about in a similar tone that one handbook that has not yet gone out of style and predictably never will is the handbook of nature. Here, in the totality of biological and biochemical systems, the problems mankind faces have already been met and solved, and through analogues met and solved optimally. So, keeping this point in mind, I will show you some very simple examples where we have developed products taking inspiration from nature, and that is already available around us. The first thing, if we look into the history, that the development of arch, you would see that the first arch was developed in India and then later on subsequently in different civilizations, and these are called corbelled arch. Corbelled arch of early civilization is found, for example, in Indus civilization where the brick was discovered, and the Mesopotamians. Then we gradually developed the perfect arch, which is something like you can see in your left, like the Rainbow Bridge of Utah, which is naturally made. So, here we have received the inspiration from nature that by designing a system in an arch form, you can actually get maximum compressive load and minimum tensile load on a system which can be used for bridging a gap. So, thus nature played a big role in inspiring us to create such a structure. If you go to some of the butterflies of a rainforest, you would see that this particular one, the sparkling cherub, it has a hue without the presence of any pigments. The beautiful color that's flashing is not because of a pigment color, but because of the polarization of reflected light. We call it structural color. Now, this concept, once we have understood it, we have been able to develop on our right concepts like on the eye highlighting, where you can use such color which will be structural color and which can create an irradiations in the system, and similarly these drinking glasses where you can have a similar system. I will come to one very interesting applications, and this is from box piece, how a particular Mercedes-Benz bionic car has been inspired. Now, box piece, as we all know, that they are the beauty of a coral island, and this group of puffer-like fishes, they actually create a kind of a paradox for us, because they are bluff body in nature. Their body is not like a highly streamlined from, if you look at it from the frontal direction, but at the same time this square like body is designed in such a manner that they can maneuver quite alright inside a coral atmosphere. So, by getting inspiration, Mercedes-Benz have come up with a bionic car design which is aerodynamic, and that aerodynamic part actually comes from the hydrodynamic design of this box piece. If you look closer to the tail, you would see that there is a beautiful array of fins, and which actually helps in terms of the streamlining of the box piece. So, that has been the inspiration in terms of the design of the bionic car by Mercedes-Benz. And you can see, starting from the skeleton of the design concept, how this complete car has been developed, keeping the box piece as an inspiration. I will come to another inspiration. This time it is a functional inspiration. Many of you might have seen that how an eggshell structure behaves. You would see that this is mostly ellipsoidal in nature, and it is highly steep along the major axis of the egg structure, but it is relatively softer in comparison to the major axis of the structure. And this type of system can be copied in an amplified piezo actuator, such that if you have a piezo stack at the center of this kind of a egg like structure, and this is along the major axis, so that it is very stiff in this direction, and then you can generate a large amplitude of deflection in the minor axis, which is transverse to the egg structure. So, that is the advantage that you can get by inspection of an egg structure. Let us also have a look into our design process, that how nature inspires us or can inspire us in the design process. Now, the thought process of a designer, we can always explain it in the form of a mind map, in which you have to have many diverse ideas and then interlink them together in the form of a unified picture, which finally gives us the way towards a particular product design. Now, this mind map of a designer is something which actually depicts the different stages of the design process, and we use it often in the beginning of the concept generation phase. If we can set up a mind map that helps us to understand the different diversities of thoughts and structures, and then how to connect these to each other. If you look at the nature, the entire thought process gets a beautiful analogy in the form of the cladogram. The cladogram actually talks about the diversities of the life forms, but how at the end they are all ecologically joined with each other, something like nature as a designer and having a mind map of her own. Now, let us come to the different phases of new product development. So, we all know that our product development starts with need statement and constraints, followed by concept generation, concept selection, embodiment, product matrix, and then we have this series of design for manufacturing, design for analysis, design for engineering, and in the central of all these is the concept generation. Now, this concept generation can be done in different ways like intuitive process and directed process. We have talked about the directed concept generation in the beginning of our intelligent product design, which is in the form of trees and axiomatic principles. But now, if you look at the intuitive process, and which is generally done in a group environment, synectics play a major role in it. And this synectics is based on a large number of nature analogy. So, in 1950, Prince and Gordon have proposed this principle of synectics, and in this process you first start with your problem and then purge the known part of it, come to the unknown part of the problem, and then stop for a moment and go towards the already solved problem in nature. And from the back side you come towards that how these problems have been solved by the nature. You distill the basic principles of it, and then you explore the analogy and come towards the front part again and develop the solution of your own. It is told that the design of the fairings of a typical rocket before deployment of the satellite by Prince and Gordon, that they have actually created an analogy with a stripping of banana. The way we explore a loose joint on a banana and we strip it out, and so that the actual fruit one can eat. In a very similar manner, the rockets at the final stage strips itself open and the satellites gets deployed. So, it is based on this synectics principle. Now, analogies in synectics is having several type of it, like a direct analogy and personal analogy. So, direct analogy is starting from some aspect in the problem, looks for any comparable or analogous situations directly. Personal analogy is what if we were an element in the problem, how would you plan to solve? And then there are nature analogy, fantastic analogy and paradoxical analogy. Now, the important point that I want to focus on is the nature analogy, where we try to figure out that what kind of situation in nature does this problem remind me of. For example, an anthill or a jungle with all the animals closely together, lungs and bloodstream and all the gaseous matter that need to be transported through the body always gives us a beautiful analogy that how to design a system such that in a congested atmosphere where there is constraint of space, we will be able to create pathways for all individual elements. So, that is based on the nature analogy of studying this type of systems. Sometimes we also say that study the bats, they reside in a cave in a very congested environment and how they come out of it. That can give us a kind of a clue of how to design transport systems in a very congested urban atmosphere. So, there are 23 synectic triggers that can be used towards this direction, and some are based on subtraction, some are based on empathize, some are based on isolation, some are substitution, and some are symbolization. So, each one of them qualitatively can trigger certain stimulus inside us in order to find out a design solution. One important point in synectics is the connectivity, that even though we can think of two different aspects which are very far away, yet interestingly they can inspire each other. Consider for example this architect Buckminster Fuller, who had first designed this geodesic architecture. He said all things, regardless of their dissimilarity, can somehow be linked together, either in a physical, psychological or symbolic way. And no wonder that Buckminster Fuller had actually inspired another scientist who got a Nobel Prize in discovering the carbon allotropy in the form of C60 of carbon, which is also like a fullerene structure, and that is why it is famous as a carbon fullerene allotropy. Now, I will give you another example of connectivity. Okay. So, this is a mood board. Okay. Designers often use this mood board of this connectivity. Okay. If we look at the mood board of one of the students, the former students of design department here, this Mr. Rohit Raghuvangshi, and then he had to do in his internship a kind of a design of a new automobile, taking inspiration from nature, and that is how he was creating the mood board. And if you look at the mood board, on the far left corner you would see that one of the things that had inspired him is a frog. Okay. Of course, he had to design a futuristic automobile, and the frog stance of almost jumping is very similar to what you call a kind of a futuristic automobile mood that he could get. Now, from there, the actual car evolution of it you can see in the right hand side corner. So, you can see that how a specific aesthetic inspiration has helped him in order to generate the mood board, and that is the final rendering of the car that he had designed. Now, then I have given you only examples. Let us try to now classify ourselves. We can say that based on the stimulus or inspiration, there are different domains of inspiration. It can be from the aesthetic domain, as we have just now seen in that example of the mood board. Then it can be in the functional domain, where we actually see, you remember that egg inspiration from the egg, that is in the functional domain. Then there can be evolution domain, how things evolve in nature. Okay. So, I will give some examples of this. And then there can be sustainability domain, how things are sustainable in nature, and today's product design has a lot of things to learn on that. And finally, the intelligence domain. So, each one of these domains, if I look at it, the aesthetic domain, the range of designs that it covers related to the color, shape, size and texture of products, and they can be inspired by nature. Okay. For example, the geodesic dome has been inspired by nature in the form of design of a tensegrity structure. The functional domain, if you look at it, here you would see that there are many examples where we have looked into how things work in nature. One of the very famous example is in terms of how dolphins hear. Dolphins are the cetaceans that communicate inside the water, and then how they emit sound and how they hear through the sonar transducer, that had inspired Da Vinci to develop a tube-like sensor in the very early days of such kind of a sonar transducer development, so that these tube can go deep inside the sea and they can hear the sound of a ship that is approaching the harbor, and from the sound they can make it whether it is an enemy ship or a friend ship. So, this is something that is certainly inspired by the dolphins in a functional domain. I was talking about the product evolution domain. There are many product evolution, the evolution that can actually help in the development of new products. One of them can be based on particle swarm optimization in robotics. So, today we have swarm robots. So, particle swarm optimization or ant colony optimization or river formation dynamics, these are all where the nature, the evolution of systems in nature can actually inspire us in terms of a product design. In the sustainability domain, we will look into the systems or organisms, how it harmoniously matching with the entire ecosystem. This is very important today, particularly when we have to think of optimal use of natural resources, keeping the global warming and the socio-economic perspectives in mind. And in the intelligence domain, which is the least explored among all these domains, here we are actually continuously trying to understand that how intelligence is manifested in nature and how we can incorporate it in our systems. All these domains I will soon tell you in a much more elaborate manner. So, let us first start with the functional domain. Analyzing the geometry of the honeycomb cells, we find that the hexagonal arrays consume minimum material to create a lattice structure, and that is something that actually functionally inspired us in terms of developing the aircraft structures, which are based on the honeycomb composites. So, the core is the honeycomb shells, so that it is very lightweight, and we have two face plates on the two sides, which is far away from the neutral axis, giving them a very high flexural rigidity. So, this is a good example of this kind of a functionally inspired structure. Now, human ingenuity is that although the first case has been directly learned from the honeybees, this case that I am showing you now, the auxetic structure, has completely come out of the thought process of us, that what if instead of having the positive cell angles of honeycomb, which creates a temple like structure, we simply put it as a negative one, creating the auxetic structure. And then the beauty that happens is that if you expand it, you are going to see expansion in the transverse direction also, which means the system is going to have negative Poisson's ratio. And such auxetic materials are used in varieties of structures today, in terms of generating a large compliant structure, in terms of generating metastructures, vibration control and shape control type of applications. Another functional example I will tell you, that is inspiration from animal locomotion. If you look at the rigid robots, which were the first group of robots like the quadruped stair climber or the snake-like robot or the bipedal walking robot, these were all rigid robots. That means they are having rigidity in their structure, and then the motors were connected in order to generate certain forms of locomotion in the system. Now, these locomotions, although they were directly inspired from different animals, but they were not the way the animals move, because in animals movement there is no motor. Animals movement is always based on the muscle, and this muscle, how can we use in terms of generating locomotion, had actually long time, for a very long time people wondered about it. In fact, the first group of muscles that came out from these kind of a curiosity is actually pneumatic artificial muscles, we also call it PAM. And then we later on understood that a compressed air that operates PAM is quite bulky to carry. So, better solutions could be in terms of something in our right that we can see, the electroactive polymers, okay, IPMCs, in which because of the electromechanical coupling we can create the muscle like deformations in the system. Now, another important example of inspiration from nature is on the sustainable design. So, there are aspects of sustainability like the self assembly. Self assembly is something which you are creating from a bottom up process. Okay. Today's entire 3D printing and 4D printing is actually based on such kind of a process, although still it is controlled at one point. I think very soon systems will actually develop from multiple points, and then the system will come up. So, manufacturing without hit, beat and treat, that is the fundamental of a self assembly process. So, that is one thing that we have to learn from nature, that how this happens and how we can design a system through this. Another aspect of sustainability is solar energy transformation. This is a product that we have developed at the SMSS lab, where it is a product in which there is a small scale solar cells that can actually transform the solar energy and recharge a battery, and similarly there is vibrational based energy harvesting system there, and there is a wind based system there. On our right we have some micro turbines which are wind based, and in the bottom left you can see the piezoelectric material which is vibration based. So, all these things together can create a successful solar energy transformer system which can be used 24 hours. The other interesting thing is the power of shape in sustainability, that by developing different types of shapes, in this case for example we are showing you a chevron architecture, so that you get a particular shape of an aircraft during takeoff in which the noise is of highest concern. So, you need to cut up the noise, and then when you are in the mid flight the energy efficiency is important and then it becomes flat. So, the shape control actively helps in terms of both noise control as well as control of fuel consumption. Quenching the thirst, water is going to be highly scarce, and you can see this particular example from Australia, that how they survive in the desert in terms of absorbing every bit of moisture through their body. So, they basically drink through their body. Now, I come to intelligence. So, what is intelligence? Intelligence is the ability to act appropriately in an uncertain environment, where appropriate action is that which increases the probability of success, and success is the achievement of behavioral goals. So, our intention is that how can we maximize the probability of success and minimize the probability of failure. There are different levels of intelligence, like the primary intelligence, which gives us the ability to sense the environment, make decisions and the control action. And then there are a higher form of intelligence, like abilities to recognize objects and events, store and use knowledge about the world, and to reason about and plan for the future. And there can be even higher level of intelligence which we certainly do not have it today, like to perceive and analyze, to plot and scheme, just like a living being, particularly the highest form of intelligence like the primates are having, to choose wisely and plan successfully in a complex, competitive and hostile world. How can we implement the intelligence? Well, soft intelligence can be of course implemented in terms of uh, nominal sensors, but enormous computational power. Okay? So, you need a microprocessor or microcontroller, and which through programming you can achieve. So, that is something that I have talked in the last lecture, but then that has a limit. So, intelligence through embodiment can actually save from the computational power. Often better, cheaper, more robust and adaptive agents can be developed if the entire agent is the design target, not just the controller. I will give you one example of the intelligent moat that has been developed today for exercise control. So, the moat has embedded piezoelectric sensors which sense the level of stresses applied on the limb during exercise, and it is connected via a microprocessor, and you can see the size is almost the size of a American small cent coin. So, how compact it is. So, this is a system in which the intelligence is embedded through the sensors, not just through the computational power. There are new issues of embedding intelligence are coming up, like morphogenesis, how to form a simple yet functional element like an embryo which gradually develops. So, can we develop something very small and the system gradually develops itself? How to dynamically reorganize the functional elements. Okay? This is also called emergent system, and how to integrate smart materials with micro electromechanical systems. These are some of the new issues in embedding intelligence. One of these is this we are talking about this emergent behavior is the reconfigurable robot with the swarm intelligence. So, we can see in this example here where people have been successfully able to develop small autonomous modules which can configure themselves, join themselves in order to create a much more complex system. So, this talk is based on all these references that I am showing you here, from TU Delft, the Synaptics reference, Bar Cohen's work on biologically inspired intelligent robots using electroactive polymers, and Janine Venus' famous talk on 12 sustainable design ideas from nature, Boeing's variable geometry jet nozzle, and of course different works of the students of the SMSS laboratory. Thank you.